Thank you very much for the opportunity to give a talk in this meeting. Our team, our team is working on optical frequency comms, and especially for applications for precision spectroscopy. Actually, I have to admit that our field of precision spectroscopy is not so quantum, and we are not really using entanglement every day. But actually, at least these tools, the frequency comms, that's also making important contributions for quantum information processing in controlling lasers and suppressing noise and so on. So that's this frequency comm that I like to talk about, but it's a little bit special frequency comms. It's optical frequency comms at very short wavelengths of extreme ultraviolet regions. So just as a brief introduction, I like to give an overview of optical frequency comms. Maybe many of you are already familiar with. So basically, optical frequency comm is a pulsed laser. It consists of regular pulse train in time domain. And not only that, the phase of the electric field has a fixed relations between one pulse and the neighboring pulses. And now if you take a Fourier transform of this electric field to evaluate the spectrum of such light source, it appears as narrow comm lines in the frequency domain, and they are equidistantly spaced. So this structure is called optical frequency comms. And the optical frequency of this each mode is given by this expression. So this represents the nth, the optical frequency of the nth mode. And this is given by n times the repetition frequency and offset frequency. And these two parameters, the repetition rate and offset frequency, they are in the typical setup of optical frequency comms. They lie in radio frequency domain of megahertz to gigahertz. That would mean this expression shows that if we want to count this optical frequency optical frequencies in the petahertz regime, you can just measure these two radio frequency parameters using counters, then you get optical frequencies out. So this makes the frequency comms a very powerful tool to measure the frequency of the continuous wave lasers. So let me explain one typical applications of the optical frequency comms. So this is the experimental apparatus for precision spectroscopy in our team. And in this experiment, we measure the transition frequency of atomic hydrogen, especially 1s, 2s transition. And we have a spectroscopy laser to derive this transition that's derived from a diode laser at infrared. We can take a frequency doubling twice to make it UV. And inside this vacuum chamber, we have an atomic beam of hydrogen that interacts with this excitation light source. And within this vacuum chamber, we excite 1s state to the 2s state. That's a two-photon absorption. And actually, during the spectroscopy, we scan this laser. Its frequency of this laser can be scanned. And we try to find out at which frequency or which wavelengths this excitation becomes the most efficient. That's the typical setup for precision spectroscopy of atomic target. So now here comes the optical frequency comms. While the scanning of this laser, for each measurement point, we like to know exactly what's the frequency of this excitation laser is. So for this purpose, we take a part of the excitation light by this beam splitter and send into the frequency measurement setup. And inside this frequency measurement setup, we observe the heterodyne beating between the optical frequency comms and this continuous wave laser. And this way, we can measure the frequency difference between this laser and one of the comm mode, and this way we can find out or calibrate the frequency of this spectroscopy laser. And with this apparatus, we can obtain, for example, hydrogen 1s, 2s transition frequency with this 15 to 16 digits. So this is a typical application of the optical frequency comms. You can use frequency comms to evaluate the frequency of the continuous wave laser. Another interesting applications of optical frequency comms is to use frequency comm itself as an excitation source for precision spectroscopy. And in this demonstration, we have an ion trap, and inside of this radio frequency power trap, we can trap the spectroscopy target. In this case, it's a single magnesium plus ions. And this is the fluorescence image of the trapped magnesium plus ion. And we can excite a transition of trapped single ion by using optical frequency comps as an excitation source. So we can scan these parameters of the frequency comps, like a repetition rate and offset frequency. And this way, we can scan the frequency comp structure in the frequency domain. And this is the spectroscopy result. So when one of the comb mode exactly matches to the absorption spectrum of this target, then we see strong fluorescence signal. And this signal repeats itself every repetition frequency because the frequency comb has a repeating structures. So basically, the next mode corresponds to the excitation of the same transition, but with a neighboring comb mode. And for this each measurement point, we can measure repetition frequency and offset frequency, calibrate the structure of the frequency comb, and this way we can also perform the precision spectroscopy. So this is called direct frequency comb spectroscopy in the sense that we don't use CW lasers to excite the target, but we use frequency comb itself to excite the target. So this is yet another application of the frequency combs. Also, another interesting application of frequency comb I like to describe here is the laser cooling. So this black line represents the cooling transition of the trapped atomic or ionic species. And we can again control these comb parameters, repetition rate and offset frequency, such that one of the comb mode exactly coincides to the cooling side of the transition. And by doing so, of course, there are many neighboring modes also addressing the same ions. But if the repetition frequency, that's the mode spacing, is large enough compared with the width of this cooling transition, then the heating effect from these other modes can be much smaller compared with the cooling effect of this tuned mode. And this way, we can also efficiently cool the ions by using optical frequency combs. We can also measure the temperature of the comb-cooled trapped ions. We can obtain almost Doppler limiting temperature. And this is an interesting technique because by using such frequency comb, that's a pulsed laser, we can address cooling transitions in a very exotic wavelengths, for example, in a very short wavelengths where we don't have a convenient continuous wave lasers for laser cooling. Okay, so all for these interesting applications of optical frequency combs, typically frequency combs has been generated by using mode-locked lasers in the infrared to the visible wavelengths. We can also try to use the conventional nonlinear process by using the nonlinear crystals, like a second harmonic generation, third harmonic generation, to extend this infrared frequency combs into UV, visible, and sometimes even the mid-infrared regions. However, the extension of this frequency combs into the shorter wavelengths below 200 nanometers has been very challenging. This is simply because there's no convenient nonlinear process. There's no convenient the solid-based nonlinear crystals that allows us to frequency convert into such shorter wavelengths, simply because no crystals are transparent in these wavelength regions. So this is exactly the wavelength region that we like to work at. We call this extreme ultraviolet regions, below 200 nanometers, and usually we work with above 20 nanometers. So now the question is how to generate extreme ultraviolet frequency combs, and this is how we produce the XUV frequency combs. So we use the nonlinear process, but not with crystals, but so-called high-order harmonic generation. And this is the strong nonlinear process of gas medium, not the solid-state medium, but the gas medium. And with this process, we can produce odd orders of the fundamental wavelengths, or the fundamental frequencies. So we can produce third harmonics, fifth harmonics, seventh harmonics, and so on. And this extends to extreme ultraviolet regions and sometimes even the X-rays. And to drive this high harmonic generation process, we start from high power infrared frequency combs. And then for this each odd orders per harmonics, we expect there is a frequency comb structure that's inherent from this infrared frequency comb structures. So let's see. So once we generate XUV frequency combs, what possible applications we can think about? So these are the list of applications that I can imagine by using frequency comms at such very short wavelengths. For example, let's look at these first applications, the precision spectroscopy for fundamental physics. There are many atomic targets like Helium-plus, Lithium-plus, Lithium-2+, and so on, also highly charged ions. There are many transitions at very short wavelengths, and all of these transitions can be described very precisely by using the theory of quantum electrodynamics. So by measuring such short wavelength transitions, compare it with the theoretical prediction of QED, we can test such fundamental theory of quantum mechanics. Also, it's interesting to think about building optical clocks at short wavelengths. And the stability of the optical clocks or the optical frequency standards is known to be inversely proportional to the frequency. So if you take shorter wavelength clock transitions or the high frequency clock transitions, we can expect we can improve the clock stabilities. I just described that frequency comms can be used for laser cooling, and it's also very interesting to extend laser cooling using frequency comms into shorter wavelengths. And as I listed here, there are also many cooling transitions for atomic and ionic species. Actually, none of them has been really used for laser cooling simply because there's no suitable laser system to address all these transitions. If we use extreme ultraviolet frequency comms, we can think about directly laser cooling all these species that will open up the new target for cold atomic physics. Not only all these three applications, I can also imagine other applications, photoelectron spectroscopy, dual-com spectroscopy. I don't have time to go into the details of these applications, and also for quantum optics at extreme ultraviolet wavelengths. For example, this high harmonic generation process just I introduced, it's known to produce non-classical light. For example, some particular orders of the harmonics can be non-classically correlated. All of these interesting features has never been investigated because it's so difficult to perform such experiment at such short wavelengths. By using this extreme ultraviolet frequency comm as a reference, we can imagine to investigate those non-classical states at shorter wavelengths. I like to have a closer look into this, the fundamental physics investigations by using precision spectroscopy. This is the level scheme of atomic hydrogen. As we all know, we can use Schrödinger equations to evaluate the state energies. If we want to have a higher accuracy, we can go for a Dirac theory. And actually, the best theory to describe a hydrogen-like system is called quantum electrodynamics. And all these theories can describe fine structures and Lamb shift and so on. And by using quantum electrodynamics, this is a simplified expression of the quantum electrodynamics to describe the state energy of hydrogen-like system. So hydrogen-like system, it's just a two-body system, nucleus and one electron. And the energy of the state is proportional to the Rydberg constant. And there's this first term that's the famous 1/n² scaling that can be also be derived from the Schrödinger equations. And there's a higher order contributions from quantum electrodynamics. And this last term is also interesting. This represents the small correction from the size of the nucleus. So with this high precision spectroscopy, it's not a good approximation to consider that the nucleus is point-like. We have to also take into account the distribution of the charge of the nucleus. That's also affect the transition frequency slightly. And by using this expression, actually we can calculate this transition frequency. That's a theoretical prediction from QED. But to do so, we have to put some parameters to this theory. I listed 4 parameters that we need to introduce to QED theory. One is the Rydberg constant. That's basically the proportionality factor to convert the atomic unit to the SI unit. So on the left-hand side, we want to measure transition frequency in the SI unit. We need some conversion factor here. That's one of the interpretations of this Rydberg constant. And fine structure constant that described the strength of the electromagnetic interaction. Also, we need a nucleus electron mass ratio to account for a recoil effect. So if the electron moves, then the nucleus has to take its recoil, and the strength of this recoil is parameterized by this nucleus electron mass ratio. And the charge radius, that's the contribution that I just described. So among these 4 parameters, Rydberg constant, fine structure constant, mass ratio, and the charge radius, these 2 parameters, the fine structure constant and the mass ratio, they have been measured very precisely with other measurement, like a G-2 measurement and the recoil shift measurement and so on. In the context of this precision spectroscopy of hydrogen-like systems, we don't have to consider the uncertainty due to these 2 parameters. We can basically consider these 2 parameters are already known. So the remaining 2 parameters to be determined from the spectroscopy research is this Rydberg constant and the nuclear charge radius. And obviously, if you have this expression, if you put 2 experimental input to the left-hand side, then you can solve this set of equations to obtain these 2 unknown parameters, Rydberg constant and the charge radius. And this is a one way to test the quantum electrodynamics. And this has been done in details for atomic hydrogen. So you combine 1s, 2s measurements, that's the most precisely measured transition, with some other measurement on atomic hydrogen. You can solve that set of equations. You can derive for proton charge radius. And this each point actually corresponds to proton charge radius derived from these different transitions. And of course, if the measurement is consistent and if the theory is correct, all these transitions, so all this measurement should point to 1 proton charge radius. And in fact, if you also look at these distributions with this error bars, these distributions can be explained simply by statistical distributions. And everything is consistent. We can simply take a statistical average of all these measurements to make 1 average data of proton charge radius obtained from all these hydrogen spectroscopy. So far everything looks healthy. In 2010, one of our colleagues measured some interesting systems that's called muonic hydrogen. And that's basically hydrogen, but the electron is replaced with muon. And the muon is a fundamental particle. It's very similar to electron, but the mass of muon is 200 times more heavy than electron. And therefore, the wave function of muon is much smaller, much more concentrated around the nucleus. And muonic system is much more sensitive to the nucleus effect. And therefore, by performing a spectroscopy on muonic hydrogen, the charge radius can be determined very precisely with a very small error bars. And actually, this looks like somewhat inconsistent with the hydrogen average data. And this is called proton charge radius puzzle. And actually, this is a very interesting observation. This can already be a hint for new physics that some new physics that cannot be described by quantum electrodynamics or the standard model. Or it can also point to some experimental errors. Maybe some of these measurements are simply not right, or maybe the error bars are not evaluated correct. So we don't really know what's going on here, and there have been few new measurements to really look into these interesting problems, and they actually look like this. So some of them point to these muonic values, some of them point to the old data, and some of them actually in between. And by looking at this, we don't really understand what's going on here, but still it has a chance to be a hint for new physics, and we are very much interested in investigating these puzzles in more details. And to investigate this further, our strategy is to measure something new. So our new target is the Helium-plus 1s 2s transition. And Helium-plus is not a hydrogen, but if you just look at the structure of this Helium-plus, it's very similar to hydrogen. Only the difference is that the nucleus charge is twice larger than the hydrogen. And basically, we can use exactly the same theoretical descriptions of hydrogen for Helium-plus. And this is an interesting new target to investigate such a proton charge radius puzzle. So here, the difference from the Helium-plus and hydrogen, I mentioned that the charge radius is different. Nuclear charge is different. And that's also interesting for testing QEDs because there are different QED contributions that scales differently with respect to the nuclear charge. And by taking V equal 2 system compared with hydrogen, the higher order contribution of QED is much more enhanced, and Helium-plus can be an even better probe for testing QEDs. Experimentally, Helium-plus is also interesting target because it's an ion, and we can use a trapped Helium-plus in the ion trap, and we have a better control in systematics compared with hydrogen spectroscopy, where they use the gaseous or the gas beam target. And obviously, the experimental challenge here is this wavelength. So the Helium-plus has a twice larger nuclear charge. That would mean the electron is more strongly bound compared with hydrogen. And you need higher photon energy or the shorter wavelengths to excite this 1s 2s transition. So we need a spectroscopy laser at 61 nanometer to address this 1s 2s two-photon transition. So this is our overview of our experimental apparatus, how to approach this interesting target. We start from very high power infrared frequency comms. We have an infrared frequency comm with average power of 300 watt. We take high harmonic generation process, try to take the 17th order of harmonics, and the 17th order corresponds to 61 nanometer that's fit to this excitation wavelengths. Once we produce 61 nanometer frequency comms, we can transport this into trapped Helium-plus ions to excite 1s 2s transition. Okay, so I like to look at this frequency conversion, how exactly we can do from infrared to 61 nanometer frequency conversion. This animation shows our setup for generating 61 nanometer frequency comms. So we have this empty cavity. It's an external cavity. Basically, there's nothing inside, but this is to enhance the average power and the pulse energy of this the original infrared frequency comms with a 300 watt average power. So we send high power infrared frequency comms into this resonator, and inside this resonator we have an enhancement factor of on the order of 100 to have something like 10 kilowatt of intercavity power. And then such high pulse energy infrared frequency comm can be focused into the cavity focus, and here we introduce a gas medium for high harmonic generation to drive the high harmonic generation, high harmonic generation process to convert infrared comms into 61 nanometer frequency comms. One trick here is to use these two infrared beams that is non-collinearly intersecting at the focus, and this way we can generate high harmonics towards the bisectric direction between the two infrared beams, so that we can spatially separate infrared frequency comms with the XUV frequency comms. This is particularly important because the way that we outcouple XUV light is via this small hole. So we need to spatially separate the XUV light from the infrared so that the XUV light can go out from this hole while the infrared beam experiences very small loss to the cavity. Okay, so this is how we generate 61 nanometer frequency comms. This is the actual setup in the lab inside the vacuum chamber, and this is the spectrum of the XUV frequency comms. We produce the XUV comms below even the 41 nanometers, and this 17th harmonics at 61 nanometer. This is the order of harmonics that we like to use to excite the 1s 2s transitions. We have about 30 microwatt of average power at this 17th order, and that should be sufficient to drive the 1s 2s transition. This is the spectroscopy setup. This is the light source, 61 nanometer light source. The frequency comm propagates this beam line and then focused into the Helium-plus ions inside the ion trap. This is how it looks like in the lab. This is the light source for 61 nanometer frequency comms, and a bit downstream here, this is the vacuum chamber that contains the ion trap to store the Helium-plus ions. And as a current status of the experiment, we produced 61 nanometer frequency comms with sufficiently high power. We have also ion trap working. We have a Helium-plus inside of the ion trap. We are currently trying to send this 61 nanometer frequency comms through this beamline and trying to exactly hit the Helium-plus ions. And that's not so straightforward task because, of course, we cannot see 61 nanometers, and we have to very tightly focus this 61 nanometer frequency comms onto the Helium-plus ions so that we can excite this 1s 2s transition more efficiently. So the more details of the current status, you can look at this paper that we recently published. Okay, so coming back to these possible applications of this XUV frequency comms, actually one difficulty here is this XUV light source under the ion trap setup, which has a very large scale and complexity, and also involves very high average power laser systems. So actually to build this spectroscopy setup at 61 nanometers, we spent last 10 years to design this and also all assemble this and trying to stabilize the frequency comm structure at such high power levels. And we have been wondering if there is any easier way to do such kind of XUV frequency comm spectroscopy. And this is our new idea that we termed XUV microchip technologies. And in this new idea, we plan to install high harmonic generation target for frequency conversion, and also the spectroscopy target, for example, the ion trap on the microchip. And then we can use the waveguide for extreme ultraviolet wavelengths to transport XUV comm into the spectroscopy target. And all of this can be installed on the microchip on the handheld sites so that we can downscale this complex setup by 2 orders magnitude in size. And for this idea of this XUV microchip, the key technology here is the waveguide that works at very short wavelengths. So this waveguide, that's basically a fiber, is a conventional technology in the infrared and the visible wavelengths, but it's not so straightforward to make a fiber for wavelengths below 200 nanometers. So here comes our strategy. We just take some materials, for example, fused silica. This is the refractive index of fused silica, and you can see that the real part becomes smaller than 1 at very short wavelengths. This would mean if we simply take a vacuum and make a hollow core waveguide, we can also confine such short wavelengths. The option for the cladding, we are currently thinking silicon, fused silica, gold, and so on. And this actually depends on what wavelengths we like to work at. This is our numerical simulation of the cavity, the waveguide mode. And according to our numerical evaluations, we should be able to get relatively low loss of 0.1 dB per centimeters at 60 nanometers. So once we have this waveguide, we can also think about waveguide with some interesting functionalities. For example, we can taper this waveguide to focus the extreme ultraviolet radiations. We can also think about curved waveguide that can be used as a mirror, or we can have a beam splitters, interferometers to make such an optical circuit at very short wavelengths. And all of these are very difficult to realize by simply using conventional free space optics, just mirrors, at very short wavelengths. But by using these waveguide technologies, we can imagine to have all these special optics. So this is our current status of the development of the XUV microchip. So for XUV waveguide, we have a collaboration with Canon, Ghent University, and IMEC. They are really specialized in making such a fine structure of hollow core waveguide with a very good surface quality. And we recently demonstrated the optical waveguides that works at 120 nanometers. For frequency conversion into shorter wavelengths, we are also testing the efficient high harmonic generation by using solid materials. For example, we use metamaterials that can enhance the field so that we can obtain even higher intensity to improve the efficiency of this frequency conversion. Also, we have to think about what is a suitable light source, infrared frequency comms, to drive this microchip. And we recently developed the very high pulse energy optical frequency comms, but with a very modest average power, because a high power laser like a 300 watt, we cannot focus into this microchip. And this high pulse energy with low average power can be achieved by reducing the repetition rate from the typical megahertz range to 40 kilohertz. And we recently experimentally proved that the frequency comb at such low repetition frequency can also be very low noise, and we can have a very fine comb structure at such low repetition frequencies. And that's a very suitable light source to drive this XUV microchip. Okay, so to summarize, I discussed many applications of XUV waveguides, and these are two experimental apparatus, the conventional free space XUV light source, and in the future we are very much interested in pursuing this idea of XUV microchip. This is our team, and the Tariq and Jorge, they are also attending this conference. If you have any questions, please also talk with them. And I thank Professor Hensch and Thomas Odem for their help. Thank you very much for your attention.
Thank you very much, Akira. Questions?
You were showing this resonator before, and you had in your animation you had 6 mirrors. Why, or is it really 6 mirrors or is it more?
No, actually, our repetition frequency is 40 megahertz, and this cavity length has to be matched to the repetition frequency. In fact, we have 7.5 meters of cavity length, and to fit this long cavity into a relatively small size, I think we have 12 mirrors or so in total. So this is a quite simplified picture. Yeah.
Okay, but the length has to fit to the repetition frequency.
That's right. Length has to fit to the repetition frequency such that there's one incoming pulse, and the next incoming pulse can overlap with the circulating pulses.
All right, thanks.
Yeah, please.
So you have mentioned that you could generate up to 40 nanometers.
Yeah.
What actually the limitations maybe of this generation? So if you, for some reason, want to go up to even higher frequency, could you go, and at what limit, like 10 nanometers less? That's
right. So it's interesting to even go for shorter wavelengths, and one of the, actually we can do so by simply having a higher intensity. We can simply change this focusing mirror with a shorter focal length. We can have a higher intensity. We can also drive to the shorter wavelengths. I think one of the limitations is that if you multiply frequency, you also multiply noise. And that's one tricky part in this XUV frequency comb generation. You have to start with a very low noise infrared frequency comb so that you still have a very sharp low noise comb structure after the frequency conversion. And this requirement gets more and more difficult if you go for a higher order, shorter wavelengths. And currently our systems allows us to generate 17th harmonics with a fine comb structure. Probably also 25th also fine, but if you really go for very high orders, the phase noise will be fundamental limitations.
Okay, thank you.
I hear that your taxi is already here.
Sorry?
I have heard that your taxi has already arrived. Are you being
my taxi has arrived, okay. Oh, okay, but I'm happy to take more. I think there are some more questions.
Hi. Is there a difference between the rectangular or square-shaped mirror and the circular mirrors which you showed? These two.
The difference between the square mirrors and the circular. Okay, so for example here, actually the shape doesn't really matter, but for example here, there's an incoming pulse, and the incoming pulse only goes into one of the beam. And one side should be partially transmissive, and the other has to be highly reflective. In that sense, this is two different mirrors combined. And maybe that's better to show it in the square mirrors.
And also, is there any theory or beyond standard model theory which predicts any oscillations, temporal oscillations of the proton radius?
Sorry, I didn't understand.
Is there any theory which predicts oscillations in the value of proton radius?
So proton radius. I'm not sure. So if you simply interpret this as a proton radius, then probably the proton radius should be constant. But for example, this discrepancy could be due to the different interactions of electron and the muons, and such differences can also appear as a difference in the proton charge radius. And that's what I mean by looking for new physics. If everything, the theoretical understanding and experiment is correct, it should point to the single proton charge radius, but maybe there are some discrepancies inside the theory. For example, the muon-electron interaction difference, or it can also be new interactions with dark matters and so on.
Yeah, I mean, maybe it's a stupid way of looking at it, but if this negative y-axis is time, then you see like the values oscillates like this.
Oh, you mean these oscillations?
Yeah.
So actually, this particular order is not too much meaningful, but recently there is indeed interesting investigation that if you list this as a function of the principal quantum numbers, then indeed there seems like proton charge radius is changing as a function of the principal quantum numbers. And indeed such behavior is expected if there is an interaction of the interaction with the dark matter, and if this typical energy size of the dark matter is on the scale of the hydrogen, then the electromagnetic interaction for the 2s state can be different from the, for example, 10s state. It can be distance dependent. Then indeed such behavior or the proton charge radius can be principal quantum number dependent. So it's a bit unclear and it's too early to say that we see that, but maybe that's an interesting direction to investigate that.
Okay. Thanks.
And proton substructure is unimportant here?
Yeah, actually proton substructures, we also into account the shape of the protons, not only the radius, but also the higher order terms. Yes.
And since you're just guiding the 17th harmonic out of a slit, aren't you worried about some sort of beating between your infrared frequency and the high harmonic frequency that you've generated?
Could you please repeat the question?
I mean, if any of the fundamental light, the infrared light, leaked out of that the cavity, aren't you worried about beating between the two frequencies at the 17th harmonic and the fundamental?
So you mean this cavity for the frequency conversion, or
the 17th harmonic cavity that you have to generate 60 nanometer light? Yeah. If by chance infrared light leaked out of that slit that you had, aren't you worried about some sort of beating between the two frequencies that you have?
So I'm sure if I really understand. So if there's an infrared with two different frequencies, is that the problem?
I mean, you have you're just guiding the 17th harmonic out, the 60 nanometer light out of a slit, right?
Yeah, here you mean, yeah.
In case like your infrared light also leaked out of the slit, aren't you worried about some sort of beating between those two frequencies?
Infrared leaking from the slit.
Yeah.
Yeah, indeed, that's a very good point. And since we have such high average power, we have a 10 kilowatt beam circulating in this, we try to separate it spatially, but there's a tiny amount of infrared leaking through this hole, and that's indeed a big problem in the spectroscopy setup, because it eventually leads to the helium-plus ions, and it introduces a huge AC Stark shift. And to prevent this, here we have a dichroic mirror, and this mirror actually transmits infrared and only reflects the high harmonics. And this way, we try to suppress the leaking infrared going into the ion trap as much as we can.
And is this all done in vacuum? Because aren't there water lines that, doesn't water absorb these UV frequencies?
Oh, this part is fully evacuated.
Okay.
Yeah. Okay, so thank you very much again for a very inspiring talk. And thanks for sticking around. We see each other at 7 for dinner and then 8:30 back here for the poster session.